Welcome to this beginner's guide on C-sharp reflection and metaprogramming. These powerful features allow you to inspect and manipulate code at runtime, enabling dynamic discovery and interaction with code elements. This is essential for building flexible and extensible applications. Reflection allows managed code to read its own metadata, which is data about data. This provides dynamic discovery and interaction with types, methods, and properties. This runtime capability is a cornerstone for advanced C-sharp programming, enabling deep introspection. At the heart of reflection lies metadata, crucial information embedded within your compiled code. This metadata details all types, methods, properties, and events. Understanding metadata is the first step to effectively utilizing reflection for dynamic code interaction and analysis.
C-sharp code follows a hierarchy. Assemblies contain modules, which encapsulate types. Each type is composed of members, including methods, fields, and properties. Reflection allows us to navigate and inspect this entire hierarchical structure, providing a detailed runtime view of your compiled code.
The system, reflection namespace, is your gateway to these powerful capabilities. It provides essential classes like type, assembly, method info, and property info. These are your primary tools for performing reflection operations, enabling general type information, assembly details, and method or property introspection. The type class is fundamental, serving as a central hub to access comprehensive metadata about any type declaration. It offers methods and properties to discover a type's name, namespace, base type, and implemented interfaces. This provides a complete picture of its definition, enabling detailed runtime introspection. Basic uses of reflection include inspecting types to understand their structure, examining individual members like methods and properties, and dynamically instantiating objects at runtime. This means you can create instances of classes whose types were not known at compile time, adding significant flexibility. Reflection enables you to invoke methods or access properties dynamically, even when their exact names are not known until runtime. This late binding is useful for plugin architectures. Reflection also allows you to discover and work with custom attributes applied to code elements, adding declarative metadata. To retrieve type information, you obtain a type object. This can be achieved by calling getType on an existing object instance, or by using the typeof operator with a known type name. Both return a type object, which serves as your entry point to explore the type's metadata. For dynamic instance creation, activator.createInstance is the essential method. It allows you to instantiate objects without directly calling their constructors, especially when the class type is determined at runtime. This is invaluable for factory patterns, dependency injection, or loading types from assemblies. Here's an example of creating an instance dynamically using activator.createInstance. We first obtain the type object for our animal class using typeof. Then, we pass this animal type to activator.createInstance, which returns a new instance of animal. We then cast this generic object to our specific animal type. Reflection allows you to access non-public members, such as private fields and methods, offering deep introspection into internal class workings. While powerful for debugging or framework development, it should be used judiciously. Overuse can break encapsulation and lead to less maintainable code. You can modify properties and fields of objects dynamically at runtime, providing immense flexibility. This means changing an object's state or behavior after creation without recompiling. This is useful for configuration systems, data binding, or tools interacting with objects whose structure is unknown until execution. To access and modify a property dynamically, obtain a property info object for the desired property from the type object. For instance, getProperty retrieves it. Then, use its setValue method, passing the object instance and new value, to update the property at runtime. Invoking a method dynamically involves using the methodInfo class. Retrieve a methodInfo object for the target method from the type object, for example, getMethod. Its invoke method then executes the method, passing the object instance and parameters. This enables calling methods whose names are determined dynamically. Dynamically loading assemblies at runtime using assembly, load, or assembly.load file significantly extends application functionality. This allows your application to load and utilize code from external assemblies not referenced at compile time. It enables plugin architectures, hot swapping components, or loading different library versions. This dynamic assembly loading and interaction is known as late binding. It is particularly useful when exact types or methods are unknown at compile time. For example, a plugin system can load various plugins implementing a common interface without knowing specific types beforehand. Late binding allows your application to adapt to unknown components. Metaprogramming is the art of writing code that manipulates other code, encompassing reflection, source generators, and the Roslyn compiler. It allows your software to read, generate, analyze, or transform code. Essentially, metaprogramming enables your software to become self-aware and self-modifying. A core concept in metaprogramming is code generation, creating new code at runtime or compile time. Runtime generation allows dynamic application behavior, while compile time generation, like with source generators, automates repetitive tasks and improves performance. Both approaches enhance developer productivity. Dynamic code modification allows injecting custom behavior into existing code without altering its original source. This can be achieved through IL weaving or dynamically generating new code. It's invaluable for cross-cutting concerns like logging, security, or performance monitoring, enabling non-invasive enhancement. Static analysis, a crucial metaprogramming concept, involves analyzing code without executing it. It identifies potential errors, security vulnerabilities, or deviations from coding standards early. Tools like Roslyn analyzers provide real-time feedback, helping developers write cleaner, more robust code. Several powerful tools facilitate metaprogramming in C#. Reflection allows runtime inspection. The Roslyn compiler provides rich APIs for programmatic interaction with C# code, enabling deep analysis and transformation. Expression trees represent code as data structures, allowing dynamic query building and code generation. The Dynamic Language Runtime, or DLR, adds dynamic language capabilities to .NET. It supports dynamic typing, where types are determined at runtime, and facilitates runtime code generation. The DLR is crucial for implementing dynamic languages and enhances C# with dynamic features. Source generators, introduced in .NET 5, are a powerful compile-time metaprogramming technique. They inspect user code during compilation and generate new C# source files that are added to the compilation. This automates boilerplate code, implements cross-cutting concerns, or generates optimized code. Metaprogramming finds numerous practical applications. A common use is code generation for database classes, where tools automatically create C# entity classes from database schemas, saving significant development time. This automation extends to many other repetitive tasks, ensuring consistency. Metaprogramming also enables domain-specific languages, or DSLs. These specialized languages are designed for particular problem domains, making it easier for domain experts to express solutions. Metaprogramming techniques allow developers to define custom syntax, parse DSLs, and translate them into executable C# code. Dynamic plugin systems are a prime example of reflection and metaprogramming. They allow applications to load and interact with new functionalities or components, known as plugins, at runtime, without prior knowledge of their specific types. This enables highly extensible architectures where users can add new features. Serialization libraries, like JSON.NET, heavily rely on reflection. They inspect an object's properties and fields at runtime to convert it into formats like JSON or XML. Conversely, during deserialization, reflection reconstructs the object. This dynamic inspection allows these libraries to work with virtually any C# object. Unit testing frameworks, like InUnit or XUnit, extensively leverage metaprogramming, particularly reflection. They dynamically discover test methods within your assemblies, identify test classes, and read attributes for setup or teardown. This dynamic discovery allows developers to simply write tests and have the framework automatically find and execute them. Advanced metaprogramming techniques include Roslyn analyzers for sophisticated static code analysis, enforcing standards, and detecting bugs within the IDE. IL weaving involves modifying the intermediate language of existing assemblies post-compilation. This allows powerful runtime behavior injection, such as aspect-oriented programming or performance instrumentation. A crucial best practice is to be mindful of performance, as reflection operations are inherently slower than direct method calls. While often negligible for infrequent operations, it can bottleneck performance-critical sections. Use reflection judiciously and consider alternatives or optimizations like caching when performance is paramount. Exercise caution with security when using reflection, especially with untrusted code. Reflection can bypass access modifiers, posing risks if malicious code exploits it for unauthorized access. Always validate the source and integrity of dynamically loaded code and apply appropriate security policies. To mitigate Reflection's performance overhead, caching reflection results is highly effective. Instead of repeatedly performing expensive lookups for type objects or method info instances, store these results after the first retrieval. Subsequent calls use cached information, significantly reducing impact. This allows leveraging Reflection's power without sacrificing speed. Always validate the existence of methods or properties before invoking them to prevent runtime errors. Reflection operations will throw exceptions if a specified member does not exist. By checking for null after getMethod or getProperty, you can gracefully handle absent members, making your reflection-based code more robust. For beginners, start with simple examples to grasp the core concepts of reflection and metaprogramming. Begin by understanding basic type information retrieval, then progress to dynamic object creation and method invocation. Gradually build your knowledge with small code snippets to solidify your understanding. Understand the performance implications and explore practical use cases to see where these techniques shine. Deepen your understanding of performance overhead and when to apply optimizations like caching. Identify appropriate contexts, such as plugin architectures or code generation, to leverage their power effectively. By mastering C# reflection and metaprogramming, you can create flexible, extensible, and maintainable applications. These advanced techniques empower you to build software that adapts to changing requirements, integrates new functionalities seamlessly, and automates complex development tasks.